Hey, good evening, everyone. This is Celso Batalha here, Astro 10, Evergreen Valley College. And this week we are focusing on the sun. The sun is our star, is the star that light up our system. And there is only one star in our system, and that is not the norm. If you look around in our galaxy, 50% or more of the stars, we know they have a companion. Imagine if we live in a system such as this. We would be orbiting a system of a double star. That would be exactly cool. We would receive different fluctuations in luminosity, in energy receiving. I don't know how life would adapt to this nice environment, but we have only one star. And the point of this chapter is to open up the sun, is to indicate what or to show what are the main regions in the sun's atmosphere, which is the outmost region of the sun, and also what are the main regions in the interior part of the sun. And and also, as we advance in this chapter, one of the points that we are going to use a lot in the following weeks, in fact, in the next 2 weeks, is the point of what is the energy production, what is the process that creates and produces energy in the sun. So the sun is a star that is very hot, there's lots of energy coming out of it, and how this energy is produced. And so we are going to focus on that. So what are the three main regions in the solar atmosphere? What are the regions in the solar interior? And what exactly mechanism is responsible for the production of energy in the sun? What keeps the sun alive? But before we go in there, in fact, today we are finalizing the discussion we had last week that was about the inverse square law. Last week's topic was based on what are the properties, how can we derive properties of stellar objects, how can we measure stars. Um, and as I and perhaps we must emphasize that astronomy is a scientific enterprise. It's not a speculative sort of a philosophical um, arena where you can come up with any idea you want and just say that's what it is. Is scientific and use the scientific method in order to produce knowledge. So, but then you might be asking, as perhaps you asked last week, if astronomy is scientific and science is based on observations and measurements, how is that possible to talk about galaxies and quasars and the beginning of the universe if in the case of beginning of the universe we were not to witness that? Certainly we were not. How can we talk about extragalactic objects when we haven't been able to leave our own solar system? How can we talk about quasars? They are so far away that we are collecting light that was sent to us sometimes billions of years ago. So how can we talk about these objects if we haven't collected yet a sample of what they are? If we can't summon these objects to our laboratory? This is a very relevant question. And so all the knowledge that you have built so far, how can you entitle that knowledge or establish that knowledge as being scientific? So here's the answer. Uh, we don't need to go there to find out what these objects are. In fact, information about what these objects are, information about their basic properties, come to us through light. So light is energy, if you will, it can be interpreted, as we saw in chapter 4, can be interpreted as a wave-like phenomena, or can be interpreted as a particle-like phenomena. But these energy carrier interacts with matter of stars, matter of galaxies, matter that happen to be in the interstellar medium. And as this energy interacts with light, it 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 collects and imprinted in itself properties of that material. Okay, and when astronomers collect this light and diverse that light and funnel that light to telescopes and to CCD, to detectors, then astronomers can use their knowledge about light interaction with matter to determine what was or what were the basic properties of the gas or the circumstellar material or the atmosphere or the galaxy, if you think about the collections of billions of stars, of all these objects, what are the properties of these objects? Because eventually this light came from some material or interact with some material. And astronomers spend years learning about these interactions so they can infer properties or basic properties of the celestial objects. So light is important in that matter. And the point of discussion this week is about the inverse square law. So the inverse square law is a law that relates, in fact, it indicates a law that is shared among other waves. Sound waves has the same property, and that is, as you go away from the source that produces the sound, or as you go away from the source that produces the light, the intensity of this light falls with the square of the distance, or the intensity of the sound falls with the square of distance. So if you double the distance from a sound source or from the source of light, the intensity of the light will fall 2 squared. So by a factor of 4. If you triple the distance, the intensity of that light will fall 3 squared, 1 over 9 from the initial intensity. So and the equation is so that, let me see if I can bring my notepad here, if I can write something here. Let me see if I can. So the relation is pretty much simple. So you have B, which stands for brightness, is equal to luminosity divided by 4, it's a constant, times a number pi. You don't need to know how this number came by, but you can ask me, times the distance to that source to the square. So this is the inverse square law basically, right? This is the inverse square law that relates brightness, which is a property of that object you observe, is the amount of energy you are collecting here as a result of that source or the star or the galaxy emitting something. And L is the intrinsic energy that source puts out. Is the amount of energy that altogether that source sends to the entire universe. And that amount of energy falls down with the square of the distance. So there are several examples where this property is applied. For instance, let's say you observe a star that you don't know how far that star is. And I ask for examples, and my students are not being able to produce or to provide a lot of examples. So I'm giving few examples that comes about. So let's say that you, oops, battery is falling down. Let me get my cable. I'm sorry, just a second. There you go. So one example, let's say you take your telescope and you put a spectrograph on it, and then you observe a star, and you find a star has emission or absorption lines, but better saying absorption lines, which probe the atmosphere, the outmost gas of that star. And by doing a very detailed analysis, you determined that star is identical to our sun. Let's pretend a case like that. So you observe a star, and the spectroscopy, the spectroscopy of that star indicates that for all purposes, the broadening in the lines, the depth of all the lines, millions of lines that you can analyze, and you can use computer, in fact, to assess that information. You don't need to stay observing and measuring and comparing millions of lines. A computer software can do that for you. And you agree that the star, for all purposes, as far as the spectroscopy is concerned, looks like identical to the sun. First thing. Second, you also do photometry, which means you observe that star in all possible color bands. And again, for all purposes, these two stars seems to be the same. So the sun and this unknown star. So you conclude this unknown star is similar to the sun in the sense that produces the same type of lines and has the same temperature and has the same color variation. And then you can say, okay, that star is an identical star to our sun. If that is true, if it is identical, that star is putting out the same amount of energy, which means the same luminosity as our sun. So this term here is given. So we know that. What do you do next? Well, you take your telescope and look at that star with your telescope, find that star, and then you can then measure the amount of energy of that star you received here. So the sun is close, so the sun is pretty bright. So bright, you don't see any star during daytime. But at nighttime, you take your telescope, point to that star, and then you can measure the amount of energy you're receiving here. So you got this term. Now you have an equation with three terms: brightness B, luminosity L, and distance D. So what do you do next? Well, you know luminosity because you assume it is similar to the sun. You observe, you have the brightness. This is a measured quantity, and then you can find the distance. So you find the distance to that star because you, for all purposes, you find that star with similar properties of our sun. And then you can apply the same inverse square law to other types of objects, H2 regions, for instance. You observe H2 regions in our galaxy, but also in other galaxies nearby. So you know the amount of energy that comes out of a H2 region. So you know the luminosity, you observe the brightness, and then you can get the distance. There are other examples, like there are variable stars, which we will start studying more closely in the next few weeks, called RR Lyrae and Cepheids. Those stars, they have a funny property. They pulsate. They expand and contract in a very consistent cadence, very consistent period. So RR Lyrae, they tend to pulsate with periods less than 1 day, and Cepheids with periods more than 2 days. So they are different, but there is something interesting about stars. It was found that the time they take these stars to pulsate, that period, is proportional to their luminosity, to their energy. So if you observe this star in several consecutive nights, you can determine their pulsating period. that leads to the luminosity. And again, you just observe the average brightness of these objects. You have B, the luminosity you have, and then you can get the distance, which is the unknown factor. So you use the luminosity period relation between these pulsating stars to assess the luminosity. You observe them, get the brightness, and then you can get the distance. And you have so many other possibilities, like supernovae. Supernovae has a very, especially type 1, has a very specific energy production when these stars called supernovae, they explode. So when they explode, the energy, the luminosity is well known because it's the luminosity of a 1.4 solar massive star. So when that energy comes out, you get your luminosity. You observe them, you have the brightness. Then you can get the distance to these objects. Okay? And there are several of these examples. You do not need to do parallax to find the distance. In fact, parallax can only be used for nearby objects. So let's go briefly exploring the sun. So looking at the solar interior, the sun's interior, the sun is a star, is 100 times as big as our planet Earth, 10 times as bigger as Jupiter, and is the only source of energy in our solar system, and is a star. So it's a star mature, and we are going to learn what that means. What does it mean to be a mature star? So this star, the sun, has a core right here, has a core, and this core is the center part of the star. That's where the energy is produced. Remember, in the beginning, I was commenting on energy production. Energy is produced in the solar core and is the result of what we call fusion reactions. Fusion reactions. Sorry, I don't have my stylus here. Fusion reactions. There you go. So fusion reactions means what? 4 atoms of hydrogen, in fact 4 protons, they fuse together and produce as a result 1 atom of helium. But there is a byproduct of this fusion reaction when these 4 atoms of hydrogen fuse into 1 helium, and that is production of a particle that interacts very little with matter. It's called neutrinos, but also produce gamma rays, produce energy. So gamma rays, as we saw in chapter 4, is electromagnetic radiation, is energy. So that energy produced in the core as a result of fusion reaction is the one that travels through the sun and kept the sun or keep the sun stable. Remember, the sun has mass, has weight, and this weight and mass tends to bring the sun to a center part to squeeze as much as possible. But this pressure, this inward force that is caused by gravity, by weight, is balanced by the pressure of this energy that is produced in the very core. So we have a tug war between 2 forces. One is gravity, and the other is the force produced by radiation, pressure on the gas itself that keeps it from falling, from collapsing. And we call that hydrostatic equilibrium, which will appear in future section. But important in all of that is the sun's core is where the energy is produced. Now, and that's also the first region. So the core is about 25% out from the center. Now, the second major region is the so-called the radiative shell or radiative diffusive shell, is where that energy finds its way to a region or to a shell very much close to the solar atmosphere. So in the radiation shell or radiative diffusive shell, that's where this energy, this radiation, and we use this word diffuses to indicate that in the core of the sun it is very energetic, it's gamma rays. But as it moves outward, that energy of the gamma rays is scattered, is interacts with gas, transfers some energy to the gas itself, and as a result, that energy loses some of its the radiation loses some, and because of scattering, the radiation changes its frequency. The radiation becomes less energetic as it moves outward. Up to where? To the less major region, which is called the convective zone. The convective zone, which is right here. So the convective zone is a region where energy is transported by a different method, is by bubbling up. So convection is a process by which there is a mass motion. The transport of energy, not transportation, the transport of energy is done by mass motion. So we have a global or a big bubble of hot gas that rises up to outmost region in the solar atmosphere, transfer heat to the cooler regions, and as it loses energy, loses heat, it falls down back to the interior regions and then keeps circulating as it kicks up and picks up more energy. So this circulation is called convection. So the convective zone is the third and the outmost region of the solar interior. So three regions: the core, the radiative diffusive shell, and the convective zone, the outmost one. So there you go. So you have about 25% or so the core, and then you have the radiative diffusive shell up to 80%, between 25 and 80%, and the outmost one is convective zone right there. Energy production is right in the center. At the core, fusion reaction. And how the energy is produced, here's an example for protons. And protons is atom of hydrogen atom. A proton without an electron is just a proton. If you take a proton, which is a positive particle, and you bind that to an electron, you have an atom named hydrogen. So hydrogen is an atom that has one proton and one electron. So if in this core of the sun, the temperature is in millions kelvins. So with such a high temperature, these electrons, they don't get bound to the nucleus. They are free to go. And which means this nucleus, they fuse, they consist of free protons. The protons are not linked to electrons, forming hydrogen atoms. Is a plasma. And these four protons, because of the high pressure, they ended up fusing. And as a result of these fusion reactions, a process which in the case of the sun has a sequence called pp chain. These four protons, they fuse finally into one atom of helium. There we go. Plus neutrino and gamma rays. and that is pretty much our solar interior. Now, we don't see the solar interior directly. We see the atmosphere. So in the photosphere, now let's think about the atmosphere itself. The atmosphere consists also on three regions. And if you go back to, for instance, this picture here, see this bubble, these cells? So if you take the atmosphere right here, this little tiny thing up there, atmosphere is 400 kilometers, it's very thin. The atmosphere is sitting on the last possible shell where convection is taking place, where this bubbling is taking place, like a miso soup. And that's what we see. See these all these little shells, little bubbles kind going up. They are called granulations. Granulations, and each granules has 3,000 kilometers, 4,000 kilometers or so of diameter. So they are pretty much half Earth size, if you will. Because yeah, yeah, Earth has a diameter of 12, 13,000 kilometers. So this is about a quarter of Earth size. So they are relatively big if you think, and if you compare with Earth itself. Bubbles are large, the size of countries on Earth. Yeah, so they are quarter size of our planet Earth in diameter. Now, this convection creates internal motion, in fact, pulsations in the solar interior. Again, you don't see the solar interior, but you can see the effect of it where this pulsation takes place. And seismology is a somewhat new science, relatively recent, and 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 these pulsations lead some shells or some regions in the sun, as you can see here indicated in blue, moving towards you, and 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 these red regions or cells going um, inside the sun. So you have this pulsation going on with oscillations of minutes or so. And astronomers have used Doppler effects to measure that. So this can be nicely measured, and then people doing theory can then use these pulsations to better constrain the solar interior. Um, with with satellites like Kepler, it opened a new door to do this type of science, not only in the sun, but in stars other than the sun, because of their um, advanced technology. So let's go to the surface. So the solar surface consists of three regions also. Photosphere is the most interior one, and photosphere is the one that emits most of the solar light. So when you look up to the sky at night time, and then you see stars in it. So those stars, the region you are really seeing are are the photosphere of all these stars. So we don't see the other regions. We don't see the stellar interior. We see only the photosphere. Is a sphere, if you will. It's not a sphere. It's a shell where this radiation is able to eventually escape the star. So just think about it. In the core of the star, electromagnetic radiation is produced. You have gamma rays, right? But this energy takes a long time. It takes 1,000,000 years or so to reach the atmosphere. And when it gets there, it escapes. But when it escapes, the color, the dominant photon energy, is not gamma rays anymore, but is optical, is yellow. The sun is a green-yellow sort of a star because the energy of the core itself was stripped off as it moved outward, helping to keep the sun stable, not collapsing. So the atmosphere, if you take a spectrum of the sun, you have all these tiny absorption lines. As you can see, these dark lines indicates transitions that are happening with specific atoms, with sometimes molecules, depends on where you look. Here's hydrogen right there, so we have a hydrogen line in there. If you go to the blue, you might have calcium somewhere. Sodium lines in another region. It might be sodium lines, I'm not sure. But so somebody studying spectroscopy can identify those transitions, and depending on how deep they are, how large they are, we can infer properties of stars that are not close to us. Now, the region above the photosphere is called chromosphere. Chromosphere. So it's the layer above the photosphere. The temperature is funny to say that it's higher, but most of the traces, most of the transitions we observe in the chromosphere, they are produced at a gas that is at a temperature slightly higher than the photosphere. So you could say the photosphere has an effective temperature of 6,000 Kelvin, and lines that are produced in the chromosphere, they go in emission at a slightly higher temperature. But I mean, it's hard to tell which one is hotter. I mean, the photosphere goes from, in the case of the sun, from 3,800 Kelvin and go all the way to 50,000 Kelvin. And the chromosphere goes from 3,800 Kelvins and increases again up to 10,000 kelvins or more if you include the transition region. So I really don't like to compare temperature. I mean, they are different. Depending on which line you're looking, you might see a different dominant temperature gas producing that particular light. Here is the chromosphere. This looks like a planet transiting Venus or so. But here is one example of a gas. So all this pinkish coloration you can see at the edge of the sun is radiation that comes out of the chromosphere. That's why the name chromosphere. It's because when they didn't know what it was, now we know it's hydrogen lines. They thought that could be chromium, had a chromium coloration or so. In the chromosphere, you can see some of these features if you can block the sun, like in a solar eclipse. Right? Now, above the chromosphere is corona. Those of you who went to see the solar eclipse, we went to Oregon. It's a great time. So if you did that, you saw that the photosphere is blocked. The chromosphere might be blocked too, but you still can see a bunch of kind of a brightness coming out of the sun. So what is that? That's the so-called corona. So corona is hot. It's a hot gas. It's not dense. It's not thick like the photosphere, but can go millions of kelvins. And because of this high temperature, it produces primarily X-rays. So most of its energy comes in X-rays, basically. Magnetic fields. So magnetic fields are generated by stars because they rotate and they have plasma. Magnetic fields are generated by motion of charges, but also planets have magnetic fields because they have a hot interior or they have ion circulation that generates this global magnetic field we observe in certain planets like Jupiter and our planet Earth. But the stars do have magnetic fields, and the best theory there is explaining its formation is the dynamo effect, which is a combination of convective rising material in the interior of the stars plus their rotation and differential rotation. And because the sun has a magnetism, we can find several magnetic active regions in the sun. And the most clear one that we can see if you have a telescope with a nice filter is called the sunspots. Sunspots are regions, when you observe them, they seem to be dark. I mean, they are not dark, they are red if you do a photometric analysis of it, because the temperature of the spots are about 4,000 Kelvin, the temperature of the photosphere itself is 6,000 Kelvin, and spots are cooler than the photosphere, and that's why they appear dark. They're not dark. So when you compare them, when you put them in contrast, then the spots seems to be dark, but they are not. They are hot gas. And why they are cooler? Because the gas that is supposed to heat up that region where the spots happen to be located, the gas is hot in its bubbling up. So magnetic field is preventing the gas from rising up and warming up that region. And as a result, it gets cooler. So when you look at spots, you're looking at regions of strong magnetic fields, stronger than the average photosphere. And then the gas circulation is hot, is frozen by these field lines. So in gas, when you study the interaction of gas and magnetism, so when the magnetic field lines are the, um, the magnetic fields can be strong enough to control the gas motion, and they hold up to ions in the gas, and then they control the motion of gas. So if they are strong enough, the gas will not move, it will be frozen. If the gas has more pressure, it will force the magnetic fields into motion. In the case of the sun, magnetic fields in those regions happen to be stronger, and then there is not so much motion, and the region gets cooler. Now, interesting aspects of the sunspots is their cycle. So as we observe, the sun goes through periods in which there are a bunch of spots, and then it falls down to a minimum and then rises up again. And then when you compare the time it takes to go from a bunch of spots to no spots, it's about 11 years. So 11 years is very consistent, is repeatable, and has been observed since the 1600s when spots were found in the sun. And now we know it's the result of solar activity. The sun has a magnetic field that changes its period in 22 years. In 22 years, the entire magnetic polarity of the sun reverses. So what is north magnetic pole and south magnetic pole, 11 years later, it's reverse. And then the north magnetic pole goes to the south, and the south magnetic pole goes to the north. 11 years later, it goes back to what it was. And then this cycle starts all over. So these are the two cycles you should kind of pay your attention as you read your book. The 11-year cycle, which is a cycle determine the number of spots in the sun, and in 22 years, that is representative of the magnetic cycle of the sun. Okay. And pretty much that's it. I'm seeing one student here. I'm going to stop taping now. If you guys want, this coming week, I have a couple of office hours, Tuesday in the afternoon and Thursday in the morning. If you want to discuss some of it, these issues, that would be cool. If you like to see some sunspots, I have it available this coming week. In the afternoon, Tuesday afternoon, I'm gonna go to the observatory and play with sunspots. In fact, tomorrow, in case the weather is good. So let me know if you want to join me. All right. Okay, I'll stop taping now and have a good night.